Okay, class, this is chapter 2. It is the chemistry of life. This chapter we will be going through specific information. There's some information that we won't be covering, but for that information you will also not be tested or responsible for it. Okay, so I'm going to make this for you to view prior to class, and then like chapter 1, we will go over it more detailed in class. Okay, this is on the first page of the chapter, basic structures of life. So you have the basic structures are matter. Okay, anything that has mass and occupies space is called matter. Okay, then you have an element. An element is a pure substance. So for example, gold. If something is gold, then it's the pure substance of gold. Another example in your book is oxygen. Okay, oxygen can't be broken down into anything smaller. It's a pure element. And then a compound is a combination of two or more substances.
Hey there, what's an element? Elements are made up of one type of atom. Gold is an element, so pure gold only has gold atoms. If these atoms of the same element join together, they can make molecules. Here's some hydrogen molecules. If different atoms join together, they can make compounds. Water molecules are compounds of hydrogen and oxygen. Mixtures are different elements or compounds that are not joined together. So how do we separate mixtures?
Created using Powtoon.
Okay, next we're going to go on into the chapter, and we are going to discuss metabolism, catabolism, and anabolism. Okay, so we're going to be moving on to page 23. Okay, some of the previous pages we're going to review when we're together as a class. Okay, the sum of all chemical reactions in the body is called metabolism. Okay, you may have heard that term before, metabolism. Someone may have a high metabolism or a fast metabolism or a slow metabolism you may have heard of. Catabolism is the breakdown of complex compounds. So something's being broken down into smaller units. Okay, in this process, energy is released. Okay, so it's released and transferred to something that's called ATP. Okay, ATP is something that is used in reactions in your body that require energy. Anabolism. Anabolism is something that builds larger, more complex or complicated molecules from smaller ones. Okay, these require energy, so they require ATP in order for them to be created, and we will be going over more in detail in class what ATP is.
As organisms live and grow, they're constantly in the process of making and breaking bonds in molecules. Metabolism is the sum of all the chemical reactions that take place in an organism. Metabolism includes catabolism and anabolism. Catabolism includes the processes that break down complex molecules into simpler molecules while harvesting their energy and storing it, usually in the form of ATP. Anabolism includes the processes that build more complex molecules from simpler molecules. The energy acquired through catabolic processes is used to drive anabolic processes. Neither catabolism nor anabolism is completely efficient, so at each step, some of the available energy is lost into the environment as heat.
Okay, now we're going on to different kinds of compounds. Okay, you have something that's called organic and inorganic. Okay, so if you look on page, let me find it. It's on page 25 in your book. It talks about compounds of life. Okay, so you have inorganic compounds. Inorganic compounds are essential to life. Examples are water, oxygen, and carbon dioxide. Okay, an inorganic compound does not have carbon in it. Okay, that is what distinguishes an organic compound from an inorganic compound. Okay, most molecules of the body form organic compounds. Again, they contain carbon. Inorganic compounds do not contain any carbon. And again, some examples of inorganic compounds are water, oxygen, carbon dioxide, and various acids and bases.
Welcome to Moo Moo Math and Science. In this video, I'd like to talk about organic and inorganic compounds. Many of the compounds found in living things contain the element carbon, which is usually combined with other elements. This large class of chemical compounds, in which one or more atoms of carbon are covalently linked to atoms or other elements, and most of the times it's hydrogen, oxygen, or nitrogen, are called organic compounds. There are several important groups of organic compounds found in living things. They are proteins, carbohydrates like sugar, lipids, which are fat and waxes, and nucleic acids such as DNA and RNA. Organic compounds can be very large and complex. A compound that does not contain carbon and is usually simple are called inorganic compounds. There are exceptions to this, such as carbon dioxide, and also this would include carbides, carbonates, and cyanides. But generally, inorganic compounds do not contain carbon. They also are more simple than an organic compound. So there we go. Organic compounds contain carbon. Inorganic compounds do not, except for...
Okay, the next section we're going to talk about is water. Water has a unique characteristic in that it is a solvent. Okay, a solvent is something that substances can be dissolved in. Okay, so if you look on page 25 under water, it has characteristics of water, and the first one, it says water is a solvent. Water dissolves more substances than any other liquid. Okay, so you have a solvent, and then anything that is dissolved into water is called a solute. But remember, water is a solvent. Water is also a lubricator. Okay, clings to different body tissues and forms a lubricating film on your membranes. And the final characteristic is water changes temperature slowly. Okay, it can be a solid, liquid, or gaseous state.
Life, as we know it, would not exist without water. Over 70% of the planet is covered in water, and our bodies are around 70% water. But why is water so important? The structure of a water molecule and the fact that it is capable of forming hydrogen bonds with multiple other water molecules simultaneously provides water molecules with some very unique characteristics. These include the ability to act as a universal solvent, the properties of cohesion and adhesion, a high surface tension, a high heat capacity, and changes in density based on temperature. Let's take a look at each of these in turn. Water is often called the universal solvent, which means that many substances dissolve in it. Water's solvency has to do with the polarity and hydrogen bonding ability of water molecules. When a salt, such as sodium chloride, is placed in water, the negative ends of the water molecules are attracted to the positively charged sodium ions, and the positive ends of the water molecules are attracted to the negatively charged chloride ions. This attraction causes the sodium and chloride ions to break up or dissociate in water. Why is this important? Since our cells are mostly water, these solutions of ions and molecules allow chemical reactions to occur much more frequently, which is an important feature to allow organisms to respond to their environment. Water molecules are also cohesive and adhesive. The hydrogen bonds in water cause water molecules to stick together, a property known as cohesion. Polar bonds also give molecules an adhesive property, or the ability to cling to other polar surfaces. Why is this important? Well, water fills the internal transport systems of plants and animals. Because of these cohesive and adhesive properties, water allows for the efficient transport of nutrients and waste within an organism. Water also has a high level of surface tension. Because water molecules at the surface are more strongly attracted to each other than to the air above, water molecules cling tightly to each other. The surface tension of water explains why it beads up on waxy surfaces and why water-striding insects are able to walk on the surface of water. Water has a high capacity for heat. What this means is that the many hydrogen bonds that link water molecules let water absorb a large amount of heat without changing its chemical state, for example, from liquid to gas. This not only stabilizes the temperature of bodies of water, such as lakes and oceans, but also plays an important role in the physiology of an organism. Since life is based on water, and the temperature of water rises and falls slowly, living organisms are better able to maintain their normal internal temperatures and are protected from rapid temperature changes. And finally, the density of water is based on its temperature. Unlike many other compounds which contract when they freeze, the configuration of the hydrogen bonds in water causes it to expand when it freezes. This expansion causes ice to have a lower density than liquid water, and therefore ice floats on liquid water. If ice were more dense than water, it would sink, and ponds and lakes would freeze solid, making life there impossible. Instead, bodies of water always freeze from the top down. The ice on the surface acts as an insulator to protect the water below from freezing. This protects organisms so they can survive the winter.
Okay, the next section we're going to go over is mixtures and compounds. Okay, so if you look on page 25 as well, under body fluids, it says the fluids in the body consist of chemicals dissolved or sustained in water. Therefore, the first step is in learning about body fluids is to understand the difference between a mixture and a compound. Okay, so compounds have two or more elements that combine to create a new substance. Okay, so an example they're using is sodium, which is the Na plus Cl. So the Na plus the Cl equals table salt, sodium chloride. Okay, a mixture is when two substances blend together. Okay, each substance retains its unique chemical properties. Okay, so example, salt when used in cooking. You use the salt, but then it breaks apart when you use it in cooking. Okay, all right. The next are solutions. Okay, types of mixtures. I'm sorry. The first one is a solution. Particles of matter, okay, solute, dissolve in a substance, which is the solvent. Okay, the solvent again is water. So the particles of matter, which would be maybe like a salt, which is the solute, dissolves in the solvent. Okay, a colloid, it's a mixture of protein and water. Okay, so this can change from a liquid to a gel. Something like that would be like a gelatin. And a suspension. Okay, a suspension contains large molecules. So if you look on page 26, you'll see the top one is the solution. Okay, the middle one is the colloid, and the lower one is the suspension.
Today we are learning about mixtures and solutions. Now, a mixture is anything made by combining two or more different substances. For example, if you've ever eaten a fruit salad, you've seen a mixture. You make a fruit salad by mixing together blueberries, raspberries, kiwis, grapes, and any other fruits you'd like. Now, a key feature of a mixture is that the substances do not react with each other. For example, in your fruit salad, nothing has changed about the fruit just because you've mixed it together. If you wanted to, you could separate out each individual fruit and see that nothing about it has changed. Now there's one more type of mixture. It's called a solution. A solution is a mixture where substances are spread out evenly. The best example of this is to think about putting a spoonful of salt into water. If you put the salt into the water and stir, the salt dissolves, making it look like it isn't there anymore. But what's actually happening when you dissolve salt in water is that the particles of salt are spreading out evenly among the water. You just can't see them anymore. In solutions, the substance that's dissolving, which here was the salt, is called the solute. And the substance that things are dissolving in, which in our example was the water, is called the solvent. An easy way to compare mixtures and solutions is to think about taking a spoonful of each. If you were to take a spoonful of fruit salad, one time you might get a spoonful of blueberries, and the next time you might get a spoonful of raspberries. Each time you take a spoonful, it would be a little bit different. But in a solution like salt water, every spoonful you would take would be just as salty. There will be no extra salty spoonfuls because it's all mixed evenly together. Now let's practice identifying mixtures and solutions together. Let's start by deciding if this bowl of Cheerios represents a mixture, solution, or neither. Well, what is the definition of a mixture? Remember that a mixture is anything made by combining two or more different substances. And in our bowl of Cheerios, assuming there is no milk, do we have two different substances? No, all that's in this bowl are Cheerios, so this is neither a mixture nor a solution. Now let's look at another bowl of cereal. Imagine pouring yourself a bowl of Raisin Bran. Well, what is being mixed together in a bowl of Raisin Bran? Well, Raisin Bran is made by mixing together both raisins and cereal. So what is Raisin Bran? Raisin Bran is a mixture, but not a solution. It's a mixture because it's made of two different substances, but it's not a solution because it's not evenly mixed together. If you were to eat a spoonful of Raisin Bran, sometimes you get more raisins, while sometimes you get more cereal. Because it's not evenly mixed, we cannot call it a solution. On the other hand, this is an example of a solution. When I take this flavor and I squirt it into a cup of water, it makes a solution. Why is this called a solution? This is called a solution because the water and the flavoring are evenly mixed together. Every sip you would take from this cup would taste exactly the same because the flavor and the water have spread out evenly. Now it's time for you to practice on your own. Here is a bowl of trail mix. What does this represent? This bowl represents a mixture. Two or more things are being mixed together, but they are not evenly mixed. If you were to grab a handful, sometimes you'd end up with a bunch of M&Ms, while other time you might end up with a bunch of nuts or raisins. So this is a mixture, but not a solution. Next, here's a spoonful of sugar being added to a cup of tea. What does this represent? Well, this would represent a solution because the sugar and tea will become evenly mixed together. Every sip will be just as sweet as any other sip. Now, in this solution, what is the solute and what is the solvent? Well, remember that the solute is the substance that's dissolving. What was dissolving in the tea was the sugar, and the solvent is the substance that things dissolve in. Here, the sugar was dissolving in the tea. So from today, remember, a mixture is made by combining two or more different substances. And solutions are a special type of mixture, where the substances are spread out evenly.
Okay, the next section we're going to review are acids. Okay, so if you look on page 27, it's acid, bases, and pH. Okay, a strong acid, it has more hydrogen ions. Okay, so if you look at the example, you have the H+, which is the hydrogen ions. Here you can see they have less. Okay, so this one has 1, 2, 3, 4, and this one only has 1. So what I want you to remember is the more hydrogen ions in a substance, the more acidic it is. Okay, so if you look under acids in book 27, page 27, an acid is any substance that releases a hydrogen ion when it's dissolved in water. Okay. Bases. Okay, bases are substances that are more alkaline. Okay, they do not have as many hydrogen ions. This is the pH scale. Some of you may be familiar with pH. If you've ever had a pool, you test the pH in it. Sometimes when you were in school, maybe before you learned about the pH scale. Okay, so the scale usually goes from 0 to 14. So the lower the number, the more acidic something is. The higher the number, the more basic or alkaline it is. So solutions with a pH of 7 are neutral. Okay, the solutions with a pH of less than 7 are acidic. So you can see 6 is milk and saliva. And then if you go to 0, it'll be hydrochloric acid. If you look at pH of 7, blood is 7.3 to 7.5. That's something you're going to be learning throughout your nursing program. And then if you look all the way towards the top, you'll see sodium hydroxide. You'll see oven cleaners, bleach. These type of things are higher on the pH scale. Okay, egg whites, those types of things. And in class, when we're actually in class, I'll show you some examples of different ways to look at the pH scale.
Thanks for stopping by. This is 2 Minute Classroom, and today we're talking about acids and bases, which are fascinating. If you're looking for the Arrhenius and Bronsted-Lowry definitions of an acid and base, I discussed that in a separate video linked here and in the description. Acids and bases are both corrosive substances that react with and damage or destroy substances they come in contact with. Acids can burn the skin and cause pain, usually have a sour taste, can corrode metals, and turn blue litmus paper red. Bases, on the other hand, have a bitter taste, feel slippery or soapy to the touch, and turn red litmus paper blue. The strength of an acid or base is measured using the pH scale. This scale ranges from 0 to 14. The lower the number, the more acidic the substance, and the higher the number, the less acidic or more basic and alkaline the substance. 7 is considered neutral, and pure H2O has a pH of 7. It is possible to have a pH greater than 14 or less than 0, but you won't come across those very often. An example of a weak acid is carbonic acid, which has a pH of 4 and can be found in carbonated beverages. Hydrochloric acid has a pH of 1 and is a strong acid, and this is the acid in your stomach that helps with digestion. An example of a weak base is calcium carbonate, which has a pH of 10 and can be found in antacids. Sodium hydroxide has a pH of 14 and is a strong base, and can be found in some drain cleaners. Strong acids and strong bases can be combined to form a salt and H2O. For example, combining hydrochloric acid and sodium hydroxide forms sodium chloride and H2O. Most people know that strong acids can be dangerous, but strong bases can also cause harm as well. Be sure to take the necessary safety steps when handling such chemicals to avoid any injury. If you learned something in this video, do me a favor and hit that like button. If you have any more questions or...
Okay, the next thing is organic compounds. So the first organic compound we're going to talk about are carbohydrates. Okay, you're probably all familiar with carbohydrates. And remember, we said that organic compounds are anything that have carbon in them. Okay, so carbohydrates on page 29 is commonly called sugar or starches. And carbohydrates are the body's main energy source. Okay, that's important to remember. Okay, the body obtains carbohydrates by eating them. Okay, your body cannot independently make carbohydrates. And they come from such things as potatoes, vegetables, rice, and they are broken down and either stored or they're used and to release energy immediately. There's different types of carbohydrates. You have monosaccharides. Okay, examples of monosaccharides are glucose, fructose, and galactose. And that is on page 29. And there's 3 boxes. The box on the left, you'll see glucose, fructose, and galactose. Then you have the disaccharides. These contain 2 sugar units. Examples of them are sucrose, lactose, and maltose. So you can see sucrose is a combination of glucose and fructose. Lactose is glucose and galactose. And then maltose is glucose and glucose. And then you have your polysaccharides. Okay, polysaccharides are complex carbohydrates. These are carbohydrates that take longer to break down. So sometimes people are encouraged to eat these so they don't break down as quickly. For these type of carbohydrates, they can break down into glycogen, which is the stored form of glucose. Okay, so this is where your body gets its energy and glucose from as stored glycogen. Okay, so just to review, carbohydrates are the body's main energy source. And glucose is the primary form of sugar that's used by the cells. Remember, glucose is a monosaccharide, and glycogen is the stored form of glucose. That is what is created when polysaccharides are broken down.
Carbohydrates are biomolecules that are composed of carbon, hydrogen, and oxygen atoms in the ratio of 1 to 2 to 1. We can represent the proportion of these elements within carbohydrate molecules with the formula CH2O. Most carbohydrates are characterized as either monosaccharides, disaccharides, or polysaccharides. The term saccharide is just another word for sugar. The prefixes mono, di, and poly refer to the number of sugars in the molecule. Mono means one, so a monosaccharide is a carbohydrate made of 1 unit of sugar. The prefix di means two, so a disaccharide is a carbohydrate made of 2 units of sugar. And poly means many, so a polysaccharide is made of many sugar units bonded together. Let's talk about monosaccharides first. Monosaccharides are the building blocks, or monomers, of all carbohydrates. Common monosaccharides include glucose, fructose, and galactose. Glucose is by far the most abundant monosaccharide. It's water-soluble, easily transported through an organism, and is the energy source for cellular respiration and the production of ATP. Fructose is the primary monosaccharide found in fruits and plants, and galactose is the primary monosaccharide found in milk. All of these monosaccharides are 6 carbon sugars with the chemical formula C6H12O6. They can be depicted chemically as either straight chains or rings. Disaccharides are formed when monosaccharides are joined together through dehydration reactions, forming what are called glycosidic linkages. Common disaccharides include maltose, which is made up of 2 glucose molecules, sucrose, also known as table sugar, which is made up of glucose and fructose, and lactose, or milk sugar, which contains glucose and galactose. Polysaccharides are formed when glucose monomers link together to form long chains. These long chains of glucose units are ideal for storing energy. The chains can be straight or branched. Plants store energy in the form of amylose, which has straight chains, or amylopectin, which is branched. Animals differ from plants in that they store energy in the form of glycogen, which is a highly branched polysaccharide that can be broken down quickly to supply energy to tissues. Other polysaccharides, such as cellulose, chitin, and peptidoglycan, serve as structural molecules in organisms. The most abundant polysaccharide is cellulose. Cellulose is a straight-chain polymer of glucose, like amylose, but it differs in the configuration of the bonds between the glucose units. Most organisms are unable to break these bonds and cannot use cellulose as a source of energy. Instead, cellulose is used to add strength to plant cell walls. Chitin is a structural polysaccharide found in animals and fungi. It makes up the exoskeleton of insects and crustaceans. Its unique properties are a result of chitin having amino groups attached to its sugar monomers. Peptidoglycans are complex polysaccharides found in the cell walls of bacteria. The macromolecule is both flexible and rugged due to its structure. Each monomer of the polysaccharide has a peptide chain attached to it. Often, we refer to carbohydrates as being either simple sugars or complex carbohydrates. Monosaccharides and disaccharides are commonly referred to as simple sugars. The term complex carbohydrates refers to the polysaccharides.
Okay, so we still have lipids and proteins to cover, but we will cover them in class because they're a little bit more detailed. And again, we will review everything that we discussed and reviewed in this PowerPoint. We will be discussing it in class as well.